Hello, how are we doing today? Very excited. We're going to be talking about execution plans today. Non-stop execution plans, lots and lots of them. Almost no slides, all execution plans. That's the whole goal. So hopefully you're in the right place and you're looking forward to it. We'll keep going here in 1 second. Just waiting for the official start time, which is in 3 minutes. Don't forget about all the other events going on with the Community Circle. You can see the links in the description. The code that we'll be going over today is in the description. Although that will change over time as I add things or modify code, you will see changes. It's being stored out in source control. I haven't updated it in a couple of weeks. Try to keep it stable for the class. So the code's all out there. The slides are out on slideshare.net, again, down in the description. And there is a live feed on the description, live chat that you can use if you want to. I will keep an eye on that as we go along for questions. If you have questions after today, you can use, there's a Discord server I set up for that. It hasn't gotten a lot of attention, the Discord server, so it may be a failed experiment. That's okay. It was something to try out as a way to give you guys a place to interact. That was the only goal, was to give it a place to interact. It doesn't look like that one quite worked. That's all right. Regardless, we'll be talking about execution plans non-stop here shortly. Just want to make sure we give everybody a chance to get settled in and logged on, and then we'll go. Okay. Moving along, we've got about another 60 seconds here, and then we'll get going officially. Good enough. Close enough. Let's just get going. Lots to cover today, so might as well get going on it. We are talking about execution plans today. Now, if you have been following along with all the videos we've done so far, this is number 7, so there's been 6 others. And number 6 was an introduction to execution plans, in which we went over some fundamental basics on how to read an execution plan. We're going to just build on that today. There's not going to be an introduction to reading execution plans today. Today we're just going to go and start mucking around inside of execution plans. That's the whole goal. My name is Grant Fritchie. I work for Redgate Software. This is my contact information. If you have questions after today and you don't want to use YouTube for comments, or you don't want to go to the Discord server that we set up and use that, that's fine. You can get in touch with me by email, you can get in touch with me by Twitter, or you can swing by my blog. I am perfectly happy to answer questions anywhere they come from. So please, please don't hesitate. You've got permission to ask me questions. This is my contact information. Use it. All right, that's it. That's all we need to talk about. Oh, if you do want an about me, I've been working in IT for over 30 years. I've written a whole bunch of books specifically around query tuning and execution plans. So there's a whole bunch of knowledge there. I've made all kinds of horrible mistakes is really what it is, and I've learned from them, hopefully. So we're not going to go through this. Execution plans, we've already gone through all this stuff. What we're going to do is we're going to start playing. We're just going to go over and start working with execution plans. So one of the things I make a point about on a regular basis is you don't want to look at an execution plan as a measure of performance. You want to look at an execution plan as a description of behavior. And so as a description of behavior, it doesn't inherently tell you anything positive or negative about the query and the data structures and your statistics and all the rest of that stuff. It doesn't give you a positive or negative. It just gives you a, well, here's what we had, so here's what we did. And in terms of performance, you should never be counting on it for performance. But we're going to read through these execution plans and get an understanding of what they are and talk about how they're working and what they're showing us. And we're also going to look at some performance metrics. All right? So, because this is all about making query tuning easier. So query tuning fundamentally comes back around anytime we start talking about execution plans. So what we're going to do is we're going to capture the actual plan. I already showed you how to do this with using Control M or toggling the switch up here, turn on the actual execution plan. And that does mean you have to run the query. Also, I've already mentioned before, but I will mention again since this is a new video, my setup on my Windows here is slightly different than most people. I've set it up for demonstration purposes. So on yours, by default, you're going to see the text above and the execution plan down below. I'm going to see my execution plans laid out across. So we're going to execute the query. The results come back. No errors or anything. And we retrieved an execution plan. Now it's a fairly simple execution plan. Let's just go ahead and do zoom to fit instead of trying to zoom in. So that should be fairly visible execution plan for you. Now the way we look at execution plans is we've got a few items that we look for on a regular basis. We do want to check the first operator to understand properties about a plan. The first time we look at a plan, that's where we go. And then we look for things like scans and seeks, certainly, because they're indications of data movement and whether you're getting more or less data movement. We're going to look for big fat pipes indicating data movement again. And then we're going to look for operators that we may or may not understand. Why is it doing this? Why did it choose to put that operator there? And so looking at this plan, we can see, there's a nested loops join, which is pulling data from a merge join, a filter, a top operation, another clustered index seek, and then the clustered index scans up here. So of the costs, the highest cost operator is the clustered index seek, which is interesting because you're thinking like, well, wait, aren't clustered index seeks good and scans are bad? Well, the fact is that in this case, there's a higher estimated cost, and we can figure out why fairly fast. For example, the actual number of rows here is 395. The estimated number of rows here is 395. And what we have is a nested loops join. And a nested loops join does for each in the top row, executes the bottom mechanism. So what's going on? For each of the 395 rows, it then has to go down here and execute the filter, the top, and the clustered index seek. That's why it's a higher cost. It's getting, instead of getting executed once, like this clustered index scan, or once, like that clustered index scan, it's getting executed 395 times. Therefore, higher cost. It's that simple. In this instance, every instance is different. It won't always be that simple. But in this instance, it's very, very, very easy to understand why that was a higher cost. Now let's start with where we should start, which is the select operator and the properties of the select operator. 1 second, so I can just pin them in place. There we go. So, anytime you're looking at a plan the first time, I recommend going here just to see the data. There's always interesting data here. It's not always going to make a big difference in what you're doing in tuning the query or understanding the behavior of the query, but it is a good place to start to ensure that you've got all the information you need. So we can see there's nothing really exciting in here right now. I mean, compile memory. It took a little bit of memory to compile. There's cost parallelism, the estimated subtree cost. It's all fairly low. This isn't a very expensive query or a very complex one. So it all ran fairly quickly. Because this is an actual plan, we can see the query time stats. And so it ran in 22 milliseconds. It ran quick enough. And, it returned the data it returned. The reason for early termination is a good enough plan found. It was retrieved from cache because, of course, it was. It was an executed query. And no shocks in here, nothing interesting. So we can stop paying attention to it for now. Anytime we're first looking at a query, though, you want to make sure that you go in there because you could see interesting bits. In this case, we don't. So to read this plan, we need to follow the nodes and understand how nodes are instantiated. Now, we went over this last week, but I'm going to repeat it here now just so we have it in our heads. The way nodes are instantiated is through a logical process. This nested loops join needs data, and it has to take data from the top input and compare it to the bottom input. So the first thing it's going to do is try to get data here. And so it's going to say, hey, I need data, which is going to instantiate the merge join. And we can tell this by looking at the node IDs. If we take a look at the properties over here, for this one, the node ID is 0. You can see that there. And so the next one to instantiate here, the node ID is 1. And we can see that there. And each one is then going to say, hey, I'm doing a merge join. As a merge join, I am taking two properly sorted pieces of data and merging them together. Do you have any data for me? Node ID number 2. You can see that. Well, it gets the data from there. It has to compare it to the data down here. So it's saying, okay, node ID 3, give me your data. So yes, in fact, it is node ID 3. So each of these nodes is instantiated, 0, 1, 2, and 3. And it just makes sense. Now the physical data flow goes more or less in the opposite direction. This now sends a row back. This sends a row back. This determines if those rows are matching. If those rows are matching, it passes it on. If those rows aren't matching, it goes for the next set of matching rows. And so it goes all the way through, matching everything up, passing it on one row at a time. When this finally gets a row, it's going to then run down here and say, hey, filter operator, do you have any rows? The filter operator is going to be node ID number, you guessed it, 4, right? It doesn't know if it has any rows. It has to go to the top operator. The top operator is going to look for node ID 5. Data, no. It's going to go to the clustered index seek. Clustered index seek is node ID 7. It sometimes skips node IDs. Don't sweat that. And that then is the first operator occurring with data down in this path. It's going to get a row of data back. It's going to pass it to the top, which selects only the first few rows. It gets a top 1 in this case, which we're going to have to understand here in a second. And then it passes it on to a filter operator. And what's the filter operator do? I don't know. We'll have to look at that as well. And that passes it back into the nested loops join. And that's the way the query runs. So it's nice and simple, and it does that one row at a time, matching, not matching, matching, not matching, running through the exact processes that we defined. The only mystery here is the top and the filter, because we need to take a look at the query. Now the query is doing select name from production inner join, and then, aha, look, there it is. Top 1. Give me the first value that matches here. This is a way of getting versioned data. So if you have multiple copies of the data and say they're ordered by date in this example, you can see that as those changes occur over time, just give me the top 1 that matches. And so that way, ordered by the date, and that way we're only getting the latest piece of data. So it's versioned data. Easy enough to understand, nothing complex. But that's reflected back in the execution plan. That top 1 is in our execution plan as a top operator. And the top operator is saying, like, hey, I don't care how many rows you get back, give me 1. Okay, cool. We now understand what that operator is and where it came from. Now, what is this filter operator doing? Why would we have a filter operator? Further interesting point, because this is an actual plan, we get the actuals and estimates. The estimated number of rows is 395. The actual number of rows is 293. So something occurred in here to reduce over 100 rows out of the result set. So what could that be? Well, let's go in here and take a look at the predicate. This is one of the things that we're doing. So what you're going to find is, as you look through execution plans, you're going to see that there's a lot of common values. You're going to see, estimated cost, estimated CPU cost everywhere. And you may not reference it a whole lot. It's going to be all over the place. But you're going to see unique values for some of the properties, for some of the operators. And frequently, those are the ones you're going to be referencing a lot. So in this case, this filter operator, what is it doing? Well, the filter operator is actually doing the join. It is doing the comparison on the start dates to ensure that they match, because we told it in the query. We'll have to close this and go back just so we can look at it again. In the query, we said where the start date is equal to, select top 1. So even if there's a top 1 that has a date that doesn't match the dates from the other table, then it eliminates that value. So we're only looking at the ones that match. So we can actually understand this entire query now based on the execution plan and the code between the two. Okay, cool. Let's take a look at an alternate plan. Now this is another way to do the exact same query. This is not a different query as such, and by that I mean the data returned is identical. In order to get the exact same data, I've just written a different query. In this case, instead of the sub-select inside of the join, I've done the cross-apply and select to top 1 and ordered by. So it's going to be a little bit of different behavior. Let's go ahead and open that up and take a look at it. Now you see, it looks like a much less complicated plan. We've got just a single loops join, not a merge join as well, and one index scan instead of 2, one index seek, and the top operator with no filter. Now, we know without even looking at it, where did the top operator come from? Well, we know we're selecting top 1, so clearly that's where it came from. Pretty straightforward, not hard to understand. Let's go ahead and start with the select operator and see if there was anything interesting in here. Again, the first time we're looking at a query plan, this is a good place to go to see if there's anything exciting. The fact is, there's nothing in here, really. This is not the kind of plan that's going to be showing that sort of information. But still, you start there to gather up the data. There's nothing worth looking at. Cool. We'll move on. No problem. That's easy. The nested loops join is pretty easy to understand. It's doing a scan of this clustered index. By the way, why is it doing a scan of a clustered index? There's no where clause, so we're not filtering data in any way or regard except this top 1 filtering, which is reflected in the execution plan as these commands, the seek and the top operator. Now, here's the whole point of looking at these two plans. Which of the two plans would you guess executed faster? Just based on the plans that we're looking at. What we have is, let's go ahead and pull them both up again. If we just take a look at the estimated plans, it'll be easier. A little more clear, a little easier to see. What we have is a select, nested join, merge, scan, and seek versus select, nested join, scan, seek. Now, based on, you ready? Based on the estimated costs by the optimizer, this bottom plan is more expensive. And we can say that by the 51% that we see right there. And this top plan is less expensive. And we see that by the 49% right there. Now, we all started this with the whole idea of like, can we look at plans and determine performance? Which one's going to perform better? Well, eyeballing the two plans, I would say the bottom plan. If I'm just looking at the plans, not worrying about the costs, just looking at the plans. Why? One scan instead of 2, one join operator instead of 2, one fewer operators that we're eliminating the filter operator. All of that accumulatively says, hey man, you should be good to go. It's going to be cheaper, faster, and better. But the optimizer is saying that the bottom plan costs a little more, that its actual cost, the estimated subtree cost of 0.1 is a little higher than the one that's 0.09. So, okay, interesting. Well, do we just rely on our eyeball and our guesses? No. And this is where execution plans will actually fail you. And so I'm going to show you why. let's take a look at this. What we're going to do is, I've got an extended events session running right now, so we can capture live data and see the queries as they run. We're going to run this query 50 times. Okay? Just so we get an average, because you don't want to rely on a single run of the query. It could hit any kind of things. Something could snag it. So we're going to just run it 50 times real quick, and there it goes. And then we're going to run the other query as well 50 times using the Go 50. And you'll notice I'm highlighting them so that we can see the comments at the top, because it'll make it easier for us to find them when we go to look for them in the extended events. This will take just a minute here, and then we're going to wait for it to finish, and we'll switch over to the extended events. Cool. 50 executions of each query. All right, so now what we're going to do is we're going to use the extended events. The way we do it is we stop the data feed. That doesn't stop the session. And now we're going to group. We'll group by statement. Okay. Wait, statement null. Uh-oh. Hang on. I think I messed up. Oh, statements for RPC complete. That's our problem. Hang on one second. Silly Grant. We just have batch completes, which means we don't need statement, we need batch text. There we go. Cool beans. Now, with batch text in place, let's group by batch text. Aha, there we go. And now let's aggregate and get the average duration and average reads. That ought to give us enough data. With that, we're going to be able to see that this one, which executed 50 times and which is exploring alternate plans, had an average number of reads, come on baby, of 810. Whereas the other one, which was in theory the less expensive plan because it had fewer operators, had an average number of reads of 1023. It actually had a higher number of reads, even though they return exactly the same data. But this is where things get interesting. The query that had the fewer operations did, in fact, on average, run a full millisecond faster. Yeah, and I know, a millisecond. But still, 50 executions, a millisecond faster. So the differences in processing between the one query and the other query actually resulted in one of them performing better, despite that the execution plan looked like it had a higher cost. Probably because the I/O looked higher to the optimizer. And in fact, the I/O was higher, but the CPU and other stuff offset it such that this one ran faster. Woohoo! Execution plans are fun. Now, what happens to this whole shebang if we put a where clause in? If we actually start filtering our data, because it really does matter. Well, let's start off with taking a look at the execution plans. It's the exact same query as up here, but we've added a where clause, so we're only looking at one product ID. We're retrieving a much shorter set of data. And what we see in the results, one row and a different execution plan. It's not the same execution plan. Now we're looking at only seeks, because we're only retrieving a single row. And we're looking at a single top operator, because we still have the top filter going on. But there's no longer, did we have to see the filter operation, because with the filter operation, with the seeks now doing the filtering, we're covered. There's nothing exciting in the select operator on this one, so we're going to skip it for this case. But you see that it's a nested loops, pulling from a nested loops and a seek, which pulls from an index seek, a top, and another index seek. All of which we can easily explain based on everything else that we've already gone through. So we're just going to leave it right there. No need to dig into this execution plan any further. Let's take a look at the other plan. We will execute it, same as before. All right, results, one row. And then the execution plan, again, just like before, much, much simpler plan. Now, instead of all of the other stuff, we're only seeing the two index seeks, the top, and the single operation. Cool. All right. Now, based on our previous experience, which one do we think is going to run faster? Well, before we test it, let's do this. Let's take a look at, hang on, let me comment that out just so it doesn't interfere with our lives. I'm not going to execute anything, but I just don't want it messing with me. There we go. So now if we look at the two plans, well, the optimizer's saying, oh man, this is easy. That bottom plan, radically faster. A lot less work to do two seeks and a top as opposed and a join, as opposed to three seeks, a top, and two joins. Easy, done, right? Easily explained, totally understandable. Okay, let's measure. Because you don't want to simply rely on these things. We're going to measure it. So we're going to run the one batch 50 times. Hang on, first we have to turn back on our live data so we can capture it again. So we will hit go. We'll execute this 50 times. Which it did pretty quick because it's only returning one row. And now we'll execute this one 50 times. Cool. Now in the live data, we've got all the stuff back. We're going to do the same thing as before. Pause the data. Group by batch text. And then aggregate. And yeah, if there was a way to automate that, I would tell you how to do it. We'll take a look at the average there and the average there. And so now we get to see, in fact, in this case, in the last case where we had what, maybe a millisecond difference, here it's down to microseconds, but it's 100 microseconds. We had 1 millisecond difference, now it's 100 microseconds, and it's 2/3 the number of reads. The reads before were a little higher, but the CPU offset the performance slightly, but here it's night and day. The reads are lower. With the lower CPU, we've got faster performance. This is pretty normal. This is pretty typical of what I see every time I run these tests. Funny enough, frequently, the first test, the top query runs a little bit faster, not by much, usually, and the second query runs a little bit slower, again, because of the I/O. Thanks for making these videos. Sure, of course. Happy to help out. I'm glad you guys are watching. And dive in here and ask questions too. And that's it. So, what did we learn? One, we learned how to walk through the execution plans in a little bit more detail, and we're going to get into some more detail on that in just a bit. Two, we learned that we do not trust the execution plan to tell us performance, that we go and measure performance. Execution plans are a tool, very useful tool, a tool that you should use, a tool that you should have available, a tool that you should understand. And you use it in combination with other tools. It's a hammer for nails, great. For screws, not so great. That's what a screwdriver is for. For bolts, not so hot. That's why we go get wrenches. Same idea here. You want to measure performance, you go to extended events. You want to understand behavior, you go to execution plans. That's it. Any questions outstanding at this point? Cool. So, what we have here is an example piece of code from Microsoft. This is AdventureWorks USP Git Manager employees. And why is it exciting? It's a recursive query. That's all. It's just a recursive query, and we're going to let it run. It's using a CTE to recurse, meaning it can call the CTE multiple times within the query, which makes it a different bit of code from the normal type of queries that we run. And so what we're going to do is we're just going to learn how to read this, because this is where things get exciting. So I'm going to keep it so we can see the code up here, but I'm going to execute it and capture the execution plan. Now, we have here a much more complicated plan than before. You'll recognize that there's a lot more going on than any of the ones that we've walked through so far. I try to keep my examples very, very simplistic, not because what you're going to be looking at when you get out in the world is going to be simplistic. It's not. It's going to be insanely complicated, but I like to make one point at a time and therefore keep the complication of the explanation down. Now this one, just the necessity of explaining what we're getting ready to explain, we got to go with a more complicated query plan. So we're off. We're going to keep reading it. Now, starting point is the same as always. Look at the first operator, look at the details. Now, we see it did full optimization, so there's nothing, complicated or really, really weird about this. The optimizer was happy. It did a good enough plan found, meaning the optimizer didn't have to do every possible permutation to arrive at what it felt was a mathematically decent plan. So it stopped optimizing and returned the plan that we have, because based on the statistics and everything else, it's a good enough plan. Now, there's nothing else we need to see here. There's weight statistics, and if we were worrying about the performance and weights, we could look there. There's query time stats, and certainly that's useful to have when you see it inside of an execution plan. But there's nothing else really exciting in this part of the plan today. Well, in this query, it's never in there. But what I mean is there's nothing that's going to distract us today. So what's the next thing we look for? Well, we start looking around to see if there's scans and seeks, right? And if we look, there's one scan right down here. So there is an index scan going on. Here, let me zoom in so you guys can see it. There is one scan going on. But other than that, there's a seek, it's a seek, it's a table, spool, whatever the heck that is. Seek. So scans and seeks, there's one scan. It's returning, how many rows? It's 1,100 row scan. Okay, probably not that big a deal. The actual cost, the estimated cost to the query is 18%, fairly high. But we've also got 18% here on this index seek. So again, that scan's not necessarily that expensive. And if we keep looking around, here's 12% for the concatenation operator, whatever the heck that is. And then there is nested loops, blah, blah, blah. And then, oh, by the way, a sort operator, 21% of the cost. Interesting. So our highest cost operator is the sort. Oh my God, we need to, whatever order by statement we put on here was wrong. So let's get rid of the order by statement in our query. Well, no, we can't. It's order by the recursion level. It's part of the process of the recursion. Sorry, we're going to have to leave it in place. So there's not a whole lot we can do about that. So you're like, well, hang on, this query tuning thing's a waste of time. No, we're not there yet. We need to understand what's going on inside this plan, because there were things that we glossed over, right? Do you know for sure what this sort operator is doing? Well, we do. We know we have an order by. And if we go in here and take a look, we can see it. So let's expand it so we can see it. Come on, there you go. And see, it's ordering by the things that we told it to order by, which is Record 1017 and Expr 1020. Oh God. Guess what? We're going to be reading execution plans, because understanding where this stuff comes from is fundamental to understanding how query plans are generated and what they are telling you. So we're going to follow through on that and figure out all that stuff. Now, we also have this compute scalar operator. Now, what a compute scalar operator is simple enough to understand. It computes new values. Okay, great. Well, what's this one doing? Well, hang on, let's take a look. This one is performing the command expr1020. Well, we saw expr1020. Cool, we know what that is, sort of, is equal to the scalar operator to string of record 1013. Okay, cool. So at least we know where one of those values came from. 1020 came from the conversion to string of 1013. What is 1013? I don't know. We'll have to track it down. Fine. So we're going to follow along logically. Node ID 0, node ID 1, node ID 2. Cool. Seeks, we know what they are. We're not going to sweat that. Nested loops join, index seek, index spool. Okay. The only time I like tooltips is for two things. Getting the description of an object and showing you guys the description of the object, because when I get the tooltip up right, I can zoom directly to where it is and you guys can read everything. It's the only time I like tooltips. Anyway, the tooltip says it reformats the data from the input into a temporary index, which is then used for seeking with the supplied seek predicate. Okay, supplied seek predicate. There's a clue. The other thing that we need to look at is the word temporary. What's temporary index mean? Temporary index means storage into tempdb. Yeah. So now we know that this thing is putting something, we don't know what, into tempdb. Now, anytime you're doing indexes, anytime you're doing execution plans, your biggest friend is frequently the output list. What is being output from this operation? Because each of these oh my gosh, expression 1024, record 1012, record 1013. Oh my God, we don't know what any of this stuff is. Now we've seen it. We've seen the record 1016 was used to create expression 1020. Aha, I remembered it. But that's all we know, and that came out of this compute scalar operator. All right, well, we don't know what any of that stuff is. Now, what's the output from this thing look like? Well, it's the same plus a column. Hey, I know what columns are. What's the output from this one? It's the same plus another couple of columns. Okay, so in other words, this joined and this joined to return data. Okay, cool, data. I know what data is. So at least now we've got this, how would you describe a bitmap operator's role within the execution plans? Depends on where that bitmap operator is being located. We're not going to get to one of those today. I'm sorry. I will have to come up with a blog post or something to go over that in more detail. I don't have an example like I can just pop up here. I'll get to that at some point. I apologize. We're going to have to hit the ones that we've got, though. So this lazy spool is temporary storage, storing something from somewhere. That's all we know. Now, the from somewhere has to be from this concatenation operator, right? That's just naturally where it's going to come from. But what's a concatenation operator? Well, let's check it out. Appends multiple input tables to form an output table. Okay, that actually makes sense. What it's saying is it takes multiple input tables. This data and this data are appended, attached, and output. Okay, cool. I get that. That's not hard to understand. All right, let's continue following the logical flow of the data. So the compute scalar, this one's computing new values. What's it computing? Oh, great. Expression 1021 equals the scalar operator of 0. Fine. What's this one doing? Oh, God. Expression 1002 is scalar operator of 0. Oh, my good gosh. I don't know where any of this stuff is coming from. We will have to find it at some point. These things are obviously seeks, nothing confusing, nothing to understand. It's hitting the tables defined in the query to retrieve some data. Okay, cool. So the data is retrieved through these two seek operations. It goes through the nested loops join. Cool. Fine. The compute scalar operator is computing two values, 1002 and 1021. We will want to remember those. If you have to, when you're reading plans, sometimes it's a good idea to write down, hey, you know, on Scalar Operator node ID 6, it output 1021. On Scalar Operator node ID 7, it output 1002. I may need to go back to look at these nodes, and having the node ID on hand is handy. All right, so the concatenation, it's going to take the data we have up here and combine it with the data we have down here. Okay, I understand that. Well, oh my gosh, what's an assert operator? Used to verify that a specified condition exists. All right, that's not exactly the most, you know, natural thing. I don't exactly understand what that means, but okay, fine. Do we see any unique properties? I mean, estimated number of rows, estimated number of rewinds, rebinds. Nah, number of executions, 1. Output list. Well, I mean, it's interesting that it's outputting an expression. That's cool. But parallel false, whether or not the thing was parallel, we would know that because we'd see the little parallel symbols. But fine. Predicate. Predicate. Okay, cool. An expression, an assert expression, is testing a value. And what's this one testing? 1023. When 1023 is greater than 25, then 0, else null. Okay. So if we hit 25, it goes to 0. If it's null, it doesn't worry about it and keeps going. All right. 25 is actually a number that we've seen before. Inner join, no shocks. Compute scalar operator. Okay, we have another compute scalar operator. This one is interesting, though. What's this compute scalar operator doing? It's creating a new expression, 1023, the one we just saw, and that is expression 1022 plus 1. This is an incremental. This is incrementing data for us. Now, what data is it incrementing? Don't know yet, but we're going to figure it out. Oops. Let's zoom back out before we move the mouse around. You guys will get seasick. All right, and now we've got this table spool operator. Great. Now, what's a table spool operator? Stores data from the input into a temporary table in order to optimize rewinds. Okay, cool. Stores data from the input. Does anyone see any input? Anywhere. Any input. Me neither. Oh God, what the heck is this thing? All right, well, hang on. Again, do we see any data over here that might help us? Estimated rebinds, actual rewinds, number of executions. Nope, 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 nope. Output list. Nope. Node ID. Primary node ID. That's new. What's a primary node ID? Well, I don't know. It's got a node ID of 4. Okay. Now this plan's pretty simple. I could probably eyeball it and tell you which one is node ID 4. But for more complex plans, you might want to try this. I right-clicked, and I'm going to click on Find Node. It's going to bring up all of the plan operator properties. All the properties, right? All of them. Every single possible property. There they all are. I'm going to go and find node ID and node ID 4. And let's find it. Node ID 4 is the index spool. Wait a second. All right, so now we start to understand a little bit, probably. This thing is going to get data, and it's using that data to feed down there. Well, what kind of query was this? It's a recursive query. It's a query that gets called multiple times. Parts of it, anyway, get called multiple times until it satisfies whatever it's doing. In this case, it looks like what we're getting is that data is coming into there and then getting reused in that second table spool operator. So if we break it down, let's do this. We're going to zoom in a little bit and go slow. The way queries work, the the way execution plans work. There's a logical flow and a physical flow. So let's follow the logical flow. Hey, I'm a select operation. Give me data. Sort operator is like, okay, well, I have to get all the data before I can sort it. I'm going to stop everything until I can sort everything. But I will ask the next guy down for a row. Next person, row, you have a row? No. Do you have a row? No, I do not. Let me go to the next nested loops join. Do you have a row? No. Do you have a row? No. Do you have a row? No, 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 no. Yes, I have a row. I am a data operator. Physically now, the data will start to flow the other direction. I am going to return my row to this nested loops join. Nested loops join goes to its bottom operator, says, hey, do you have any rows that match this? For our example, let's say yes. Yes, I have data. Passes it back up. Passes it to here where it generates an expression. Passes it here where it generates an expression. Goes to the concatenation operator. The concatenation operator is a operator that combines two tables. Okay. The next table is, hey, do you have a row? The assert's going to check, check. Table spool, do you have a row? I don't know. Let me go check with my parent, who is over here. Now, we're at the concatenation operator. Has the parent operator gotten a row yet? No. The concatenation operator has not passed rows to the index operator. Therefore, what does child down here say? No, I do not have a row. No, no. And if there's a no here, it doesn't bother doing the loop. The assert doesn't have an operator. The concatenation operator says, okay, no more data here. I still have a row from that top query. Cool. I will pass that on to the index spool, which then goes through and does the rest of the processing, pulling data out. And now the sort operator goes, okay, that's great. Do you have any more data? Because, you know, it's one row at a time. Do you have a row? Do you have a row? Do you have a row? Right? And it goes back through. Same process, exactly the same process. Gets to the concatenation operator. Concatenation operator goes down to that lower set. Do you have a row? Do you have a row? Gets to the table spool. In this case, the table spool again. Let me check with my parent. The parent now has a row. Returns that row to this table spool operator. You get then, whatever this comparison is, oh yeah, this is the expression 1023 plus 1, so this is incrementing. That does that incrementation. There's now data. You get down here, it does this scan and the seek and the filter operator on the scan. The nested loop operator occurs. This compute scalar operator, which is taking one of the values and adding one to it. And then it all comes back up to here, and the assert checks expression 1023, which we generated here, which is incrementing. It makes sure that it's less than 25. So what is that? The max recursion rate. And we can check that by going and looking at the data. At the query. And there it is. The max recursion rate is 25. And so now we know what that operator is doing. So when we look at this plan, we can now see that the way it's satisfying the recursive process is it's creating an index spool, a storage in TempDB. That then waits until it gets data from the main part of the query. If it gets data from the main part of the query, great. It's stored on temporary stuff. The second pass, the second iteration, when I go to get my children, because it's what the query is all about, is give me children, give me children. Well, the children have to check with their parent in each case. And so in each case, this thing is going, hey, do you have a row? Well, I have to go back up here to my primary node ID, right? And I will get that data and return it back down to you. And so now we see what almost every one of these things is. And we see where the first time the full output list, I did skip over this, I don't know if any of you noticed, but the full output list of all of those different things that it's checking are all right there. And so it generates a new set of columns based on the concatenation of the top set of columns and the bottom set of columns. So all of that stuff goes out the door, and it gets aliased, and you can see the names. When it gets finally output, it will get returned to you as a data set that you can actually read. But while it's going through the execution plan, it gets all these funky tags that you can then track back through the execution plan. Again, understanding that the tags themselves and the node IDs themselves have a logical flow, meaning left to right, right? It's coming left to right for the logical flow. But then the node and the data have got a physical flow, right to left. And knowing that, you can easily say, well, data has gotten to that concatenation point the first time through, but not yet gotten to that index spool. So then you understand why, when it comes down here, it would return no data. And you get a really good understanding of exactly how this thing can walk through and do the stuff you've asked it to do. This is how we understand what execution plans are telling us, is walking through and identifying all the things that we just did. The unique sets of properties within the plans themselves, the node IDs so that we know how that they're being instantiated, and then the comparisons between the operators to see what each one is taking as input and what each one is providing as output. This is reading execution plans. This is it. It's just that simple. And I know that didn't sound simple, but it is. It just takes a long time and a lot of repetition to get good at it. Cool. We beat that query to death. Let's go beat up on another one. Let's do column store indexes because it radically changes some behaviors inside of. Let's make sure. Cool. Just want to make sure it wasn't there. I sometimes forget to clean up after testing things. Now let's take a look at this execution plan. Now it's running pretty long because the data that's doing, it's doing a lot of aggregation, summing, counting, averaging. So there's a lot of execution time involved here. Okay, it finished up. Thank God. Now the elapsed time on it was what? 14.159 seconds. You can see that over here on the elapsed time on the properties of the query itself. That's from lesson, what, 3, 4, something like that, of this whole session. So we got an execution plan out of it. Let's go take a look at the execution plan. Now, in this case, we've got a much more complex execution plan than we've had in the past. We are looking at parallelism here. You can tell very easily because all of the operators have a little parallelism tag on them. That little, 2 little arrows in yellow lets you know each operator that is in fact parallel. And the reason being is that it's moving. You can see the great big fat pipes. It's moving a lot of data. This is how many? 1, 2, 3, 1, 2, 3, 31 million rows. Okay, so it's moving quite a lot of data. 31 million rows are getting moved around and finally getting aggregated. Now, I'm not going to walk through and read this entire plan because the concepts are pretty easy. We will take a look at the properties on the first operator for sure. And we'll look at a couple of the operators just to see some differences that occur within a parallel plan. So the first operator, full optimization. Nothing, oops, there. Full optimization. Nothing interrupted the optimizer. The optimizer went through its full process. It didn't error out. It didn't, time out. It did a full optimization. But you'll notice there's a property missing. Reason for early termination. There is not always a reason for early termination, meaning the optimizer did not terminate early. It went through all of the optimizations it could try, and then at the end of that, looked at what it had and mathematically determined, oh yeah, this plan probably was good enough. Cool, I will return that plan for them and off we go. So full optimization, great, good to know. Just you won't always see the reason for early termination, just so you know. Now, parallelism. This is great because it gives us some idea what's going on in parallelism. Now this one is the gather streams node. It's not going to be as interesting. So let's take a look at this one. This one's actually better. What we can see is the batches. We get to see how it's broken down and created multiple threads. This is a small machine. There's not a lot of threads on it. But it broke out into multiple threads and ran this. And that's based on the idea that if it can throw CPU at the problem, it can speed things up. And so, you know, it generally did. But you can actually look at each one and see how did it deal with the number of rows that it was dealing with. And largely what you're going to see is the threads are going to be roughly the same between them, but not always. You're going to see differences because each one is going to be doing different operations, and therefore the rows could be moved between the streams depending on the operation in question. Okay, cool. That's, you know, useful information, but here's the deal. Aggregate queries are horrible unless you're using a clustered column store index. Let's just go ahead and execute this, get a column store index in place. It'll just take a second. No questions currently. Cool. Did it finish? Oh, no, not quite. Almost there. Okay, it's taking a little longer than normal today. I hate when that happens. Come on, hurry up. We need you. Probably should just create 2 sets of tables and cheat. Let's go. They're waiting. If I was recording the video and it wasn't live, this is where I'd pause, wait for it to finish, and then come back in and say, see, it was quick. Teasing. Totally teasing. Well, maybe. I probably do it sometimes. Wow, that is taking way too long. Let's give it another couple of seconds, though, because this is worth exploring, because there's a couple of points about reading execution plans that are unique, currently unique. It will change. It will change to column store indexes, so we need to get on top of it. Come on. Wow. I'm blaming you guys. You're watching. It's like watching a pot boil. Well, that's painful. I really want to make this point. We're going to wait another second or two. Yay, thank God. Whew, all right. With that done, let's rerun this query and capture the execution plan again. Now, if you remember, the first time we ran the query, it ran in over 14 seconds. And this time, it ran in 2. So why do we like column store indexes? Well, that's one of the reasons we like column store indexes. Take a query down from 14 seconds to 2, 7 times faster. It's kind of nice. Now, I've had someone ask me before, so I really want to emphasize this. Well, if column store indexes are faster, why don't we just have everything be on column store indexes? Well, because column store indexes are faster at aggregate style and analyst style queries. They are not faster at point style queries. They are slower at point style queries. Give me 1 row, give me 1 row, right? Little things needed for yeah, no kidding. Yeah, create the column store and then reset it. Yeah, good idea. Probably do that next time. Thank you. Good input. I agree. But for point lookup, they're slower. So there's not like something magical about them. It's like, oh, put them on and everything is faster all the time. No. They're faster for certain types of queries. But let's take a look at the execution plan, because the execution plan is fascinating. This is where things get fun. Now, it still went parallel, still parallel execution. And I know some people are freaked when you say parallel, but we're aggregating 30 million rows. Parallel is where this ought to occur. And you can tell that at least in this instance, the performance was pretty good. It went from 14 seconds to 2. That's taking advantage of parallelism. But the plan's pretty different. You notice there's not all that crazy stuff going on inside the plan. The main things we're going to focus on are a couple of things here. First up is this. Now this is column store index scan. Okay, cool. What you won't see is a column store index seek. You'll only ever see column store index scans. Let's look at this. Number of batches. Actual number of locally aggregated rows and actual number of rows for all executions. Now, what's going on? The thing is that this is going in what is called batch mode. Now that's different. Everything we've seen so far today has been row mode. You'll notice the way I keep describing it over and over again. Give me a row, give me a row, give me a row. Batch mode processing is inherently different. Batch mode processing is give me thousands of rows, give me thousands of rows over and over again. And then it figures out how many rows it can return. Now the interesting thing is that you can see it. There were 36,000 batches to return the number of rows it returned. Now 36,000 batches means it only executed stuff 36,000 times instead of our full-blown 300 million times. It also gives us a quick little bit of math. The batch size is approximately 100,000 rows. It's not exactly 100,000. It's a little bit less most of the time. But if we do the math, 36,000 times 100,000, we get to, 300 million. Is that right? Yeah, 3 zeros. Cool. So we can see that it gets real close. So you can understand that it's actually breaking those things up. So what's going on inside this execution plan is it's not, I am a select statement, give me data. I'm a parallelism string, give me data. I'm an adaptive join, and we'll get to what that is in a second. Give me data. And it's like, give me a row, give me a row, give me a row. It is, okay, I'm an adaptive join. Give me 10,000 rows if you have them, or 100,000 rows if you have them. The next one's give me 100,000 rows, give me 100,000 rows. It radically reduces the amount of processing. It does batches of data for large data sets. This is a great leap forward in processing mechanisms within queries. Yay! And we're going to see more of it in more places because they're figuring out other ways to use it. Now, a couple of points. We also saw the number of rows is 300 million, right? But it only returned aggregated 1.4 million. What's going on? Well, this thing did what's called a push-down aggregation. Because of the way data is stored on column store indexes, we can do a lot of aggregation at the point of data retrieval. So we don't have to aggregate everything through processing. We can aggregate some things just at the point that we retrieve the data, speeding things up, reducing I/O, reducing processing costs, and reducing the amount of data that we are then spitting across the wire. Because here, it estimated 300 million, but it actually did a little less than 300 million because it was able to aggregate that data ahead of time. Then the hash match does the additional aggregations that are necessary for our group by processing to occur, and its output is 25,000 rows, which is what matched the estimates, which is cool. So we've seen the way this thing changes fundamental behavior of the column store index. There's one more, and that's this adaptive join. This thing is fun. This is a fun, kicking, really cool thing. It's also proof of the fact that every single execution plan is an estimate, what we used to call an estimated execution plan, not a different kind of plan. Every one is, there's an execution plan and there's an execution plan plus runtime metrics. And the adaptive join is proof of that, positive proof of that, because it shows you both of its possible paths through the data. And that's the trick about an adaptive join. It has two possible paths through the data. Path number one is on top. That's up here. It's the index scan. Path number 2 is down here, the clustered index seek. Now, this one chose to do the clustered index scan. How do I know? Actual number of rows. It returned 25,000 rows down here in this scan, so it did the adjoin that way. Adaptive joins are limited. They will do either a hash match or a loops join. And adaptive joins are not as efficient as either a hash or a loop, but they are radically more efficient than a bad choice on a loop or a bad choice on a hash. Best of both worlds. And the thing about best of both worlds is you make little sacrifices to get there. So the way it works, and this is where things get fun, this adaptive join has a threshold, and that's right here. The adaptive threshold rows, estimated 1989.93. The way it works is it will start taking in data. Same as before. Give me 100,000 rows, give me 100,000 rows, give me 100,000 rows. No differences there. Cool. It starts bringing in data, and it starts storing it in temporary storage. If it passes the threshold, it moves that data into a hash table so it can start building a hash. And that's where it actually has an overhead. Is it has to move those 1900 rows into a hash, and then keep going from there. That's its added overhead on top of a hash. But if it was below 1900, it's like, okay, give me data, and we're all done. It goes, okay, cool, I've got less than 1989. Or 1989 or less, because 0.93, you can't get 0.93 rows. As soon as it hits that 1889, it goes, cool, I just take that little bit of data and I pass it down to my loops join and says, this is your top input now. So it doesn't have to rebuild the top input for the loops join. So therefore, it helps make the loops join a little more efficient. Not as efficient as a true loops join, because a true loops join would just be feeding the data through as it goes. And this thing has to wait until it gets all the data. But it's still more efficient than a bad hash join in the same place. So that is the adaptive join in operation. And you guys can see it all. And it's great because you can only tell which way it's going to go based on an actual plan. If we take a look at the estimated plan, it shows the same things, but we don't see the actuals, and therefore we don't see what's going on. Now I say estimated and actual because those are what's on the screen. The terms I prefer to use are execution plan and execution plan plus runtime metrics, because those are much more clear than saying estimated and actual, because this is the same plan as you saw. This is the identical plan. Heck, let's take a look at the properties on the select operator. Where did we get this plan? Retrieved from cache is true. That's the plan that was used to execute the query earlier. So this plan is retrieved straight from cache. This is the execution plan. It just doesn't have any runtime metrics because we didn't execute the query to gather those and add them to the execution plan. Cool. Oops. All right. Any questions on that one? All right, I'm not going to drop the index. I'm going to try to remember what we did and do it the same way next time. Cluster column story, we don't need to prove that that's better. Parameter sniffing. Yeah, let's do parameter sniffing. How are we doing on time? A little over. We'll keep going. I've got material. I've probably got a couple of hours worth. We're not going to do 2 hours, but we will keep going for a little while. I've got a very simple store procedure. It's not complex, intentionally kept simple. We're going to execute it to make sure it's there. Awesome. Now, I want to capture the execution plan, and we're going to take a look at it and look at a few things intentionally with some forethought. Now, the plan itself Simple enough plan. The merge join is pulling data from an index scan. It's doing a sort, which pulls from a nested loops join, a seek, and a key lookup. Tuning opportunities, sure. Key lookup operator could be, fixed by changing the key on the index seek, or creating a new index with a different key, or adding include columns to the index seek. You know the drill in terms of query tuning possibilities. Cool. That's not the point, though. The point is parameter sniffing. Is there evidence of parameter sniffing inside of an execution plan? And yeah, there is. Remember, I always say we start a plan at that first operator. Well, that has the parameter list, and it shows you both the runtime value and the compile time value. And why does that get interesting? Well, let's pluck this plan out of cache. Right, we're going to run dbcc freeproc cache and pass it the plan handle. So instead of nuking my entire plan cache, it just replaces the one plan out of the plan cache. Cool beans. Off we go. Now when we look at the plan, completely different execution plan, right? Utterly different. Why? It recompiled it for a different set of values. And if we take a look, we can see those values. Again, stored with the plan. The parameter runtime value and compile value are the same. But now what happens? Well, we go back up here and we execute this query, which we know returned quite a lot more data. And we take a look at the execution plan, and it's using that same plan, but it's moving a bunch more data for more costs. And here's the fun, or no, in this case it's less data. 72 out of one row, 7,200% greater. In short, oh no, it is more data. Yeah, sorry, got it right the first time. It's moving more data. Therefore, the plan it has, even for something as small a difference as one row versus 72 rows, the plan itself is wrong for those things. And if we want to start to investigate how and why, we go over here, because this is going to give us the parameter compile time values. Why do we care about the compile time values? Because we can take the compile time value, reference order ID, value number 41798, and we can take that to our statistics. Oh yeah. And look at and see, well, how many rows estimated is going to be returned by that value? And the fact is exactly one. It's one of the, in the histogram, it's one of the steps, and it's a step that returns a single row. And so by picking that one, I was able to cheat and make it so it generates two different execution plans with two different sets of behavior based on a 71 row difference in data. And that's all it takes. That's why sometimes bad parameter sniffing can be such a problem, is because it doesn't take radical amounts of data, 1 versus 1 million. Nah, 1 versus 72, and we saw differences in the execution plan. But the key is to go in and get the data from the parameter list. And yeah, this one has one parameter. If there were 20 parameters, they would all be there. And I think that's the last point I want to make on that. Anybody, any questions have come in so far? Nope. Cool. Awesome. Well, if everybody wants to stick around, I've got time for one more. Let me see. Do we want to do that? No, we did that one. Cool. Let's do this one. Now, this is just simple window functions. There's nothing crazy about it. Row number over, partition by customer ID, order by order date as row number, just to get the number of rows within these values. So let's execute it. Take a look at the data. So you get to see the row numbers, 3, 2, however many rows, and match each one of the data as laid out. Okay, cool. Useful information, great way to run queries. The windowing function is excellent. The execution plan is actually not crazy looking. except that it's a bunch of stuff that we don't know what it is or necessarily why it's there. Now, looking at it, again, we would start with our first operator, but there's nothing exciting in here in this case. Full optimization, good enough plan found. By the way, if it sounds like those are two of the values I look at almost instantly, they are. I will frequently get plans from people online asking me to look at the execution plans. By the way, feel free to send me your execution plans. And I will look at the plans, and the first thing I do is take a look at the optimization level and whether or not it timed out. No timeout, full optimization level. That gives me some information about your database and about the query. The main information it gives me about your database and query is that probably you've got decent indexes and or the query is not terribly complex. If you have good enough indexes, the optimizer has enough tools, it can make some good choices. When the optimizer times out, you've either got a stupid, insane query, which is possible, or I get timeouts on simple queries all the time. Stuff I set up intentionally that way so they do time out. And these queries are not complex, but they're doing stupid stuff against the structure that I have. There's either missing indexes, bad statistics, missing statistics, all of those things, no primary keys, no foreign keys, or the foreign keys are not enforced, right? All of these things impact the way the optimizer behaves. As soon as you impact the way the optimizer behaves, you're making the optimizer work harder. The more work you make the optimizer do, the more likely you're going to get a timeout. What's a timeout mean? It means you have a plan that's probably less than optimal. It'll work, guaranteed. It'll return the correct data, but it's not going to return the correct data in a fast fashion. And you can see this on a 3-4 table join. You can get timeouts if there's not a good structure in place. It doesn't have to be these incredibly complex queries. Just something to know going forward. So anyway, this thing had good enough plan found, so we're not going to worry about that. Then we would look at costs. Index scan. Well, obviously, let's take a look at the query again. Well, there's a where clause, but what else do we see here? Yeah, name a missing index. By the way, just to show you, the missing index that you always see at the top of the screen, it's only the first one. In this case, there is only one, but you'll notice this says missing indexes. And in fact, if there is more than one possible index, the optimizer lists them out here. So if you're used to looking at that little top thing on the green and going like, cool, I've got the index, yeah, you might be missing some. So it'd be a good idea to learn to look in here and pick that up. So, cool. Yeah, so there's a missing index. It probably would increase the performance on this query a whole bunch. It's not going to change anything necessarily beyond this, because the rest of the operations, the sort, segment, whatever that does, the sequence operation, and the other sort are all needed to fulfill the query. Now the first sort operation. Now sort operators, you say sort, everyone knows immediately what's going on. But the question is always the same. What is it sorting and why? And so we're going to zoom in down here and see that. Oh, come on. All right, we'll try it this way. I do hate it when it fights me on display the information I want the way I want. All right, there it goes. It's customer ID and order date ascending. Okay, customer ID and order date ascending. We regularly will have to cycle back to our query, so we're going to go back to our query and take a look at it. Row number and order date. Okay, cool. I know what that is. That makes sense. So it's ordering the data by that order date. Okay, cool. That sort operation makes sense, right? We know what it's doing. Cool. Segment. Now, this is one of my favorite tooltips in the world. The segment operator does a segment. Yeah, I think there's a developer at Microsoft needs a beating. Anyway, what does the segment operator do? Well, it has what's called a segment column. In this case, segment 1002. 1002? Well, okay, where did that come from? Well, let's go back and take a look. Is it in our order by commands? Nope. Is it in our clustered index scan? I promise you it's not. Okay, well, hang on. Where is there any kind of other command here? Oh yeah, look, group by. So it's grouping by this data. What's it grouping by? The stuff over here in the query. It's grouping by the partition values. Okay, cool. So that's what's creating our segment. Great. Now, what's the sequence thing doing? Well, it has to create an operator row number. Operator row number? Oh, it's creating our row number values for us. Okay, cool. And the output list, what's it got? There it is, expression 01. So it's adding in our output list. And then our final sort operator, what's it sorting by? Expression 01 descending and our order date. Expression 01 descending, hang on. There it is, expression 01, row number, descending, and order date. Oh, cool. These things are all read exactly the same way. It's always a question of breaking down the query behavior itself, combining it with what's going on inside the execution plan, showing you things that are like going, what is this? Why is it there? But drilling into the details quickly begins to tell you what's going on. You just have to look for those unique properties. And you know, there's not like somebody who's, maybe Hugo has, I don't think he has, that marks every operator and marks them whether or not they're unique. But maybe that would be the thing to do. But anyway, you start to look for these operators properties and understand that that's where you go to get this data. Not with the tooltip. The information is frequently incomplete. You know, here's the sequence operator. We get the output list, but what's it sequencing on? We've no idea. We need to have all that stuff, otherwise we don't know what's occurring. So you've got to drill down into the property sheet. This is why I tend to tack this thing open all the time I'm working. All right, we're going to skip down to a couple of things just in case you haven't seen it. Right. Let's just see what's going on. All right, status is 0. Let's turn it on. Turning on a trace flag 7412. I could also turn on an extended event session, do the same thing, but I don't want to. What we're going to do is we're going to take a look at live execution plan. All right? This is include live query statistics. Okay, cool. Those who haven't seen it before, you may go ooh and ah. You may not. But what's going on is, you see the little dots moving? Little ants crawling across the screen? That's showing me each of the rows processed by the query as it's being processed. And it finished, so we don't need to keep looking at it now. But I'll show it to you again. There we go. So this is processing the queries in real time, showing you each of the rows as they go. Now the thing is it's not necessarily all that useful, because how do I get it? Well, I have to go in here and say like, well, give me this, give me that, you know, and like, here's this one. Let's run this one. I don't think it's faster. I think it's slower, but let's just try it. Oh no, it's slower. Go in here and give me the execution plan and then run this. It's not useful, but let's stop it. If you've got that trace flag on and we turn off, let's not capture any of the execution plans. We're not capturing execution plans now. But I've got that trace flag enabled, 7412. Now I execute the query. Now I'm going to do something I wouldn't normally do. Let's go to my server. Come on. And let's take a look at Activity Monitor. I don't normally use this, but Let's take a look at active expensive queries. We've got a query running right now. Let me take a look at the execution plan. Yeah, if that trace flag is enabled on your servers, you can take a look at execution plans on the fly. Oh my, yes. 2016 and up, by the way. But you can take a look at execution plans on the fly and see what's going on. And this thing's processed, 12% of the rows, 15% of the rows. Now, these may not be accurate estimates, so you may not see this thing really doing what it says it's doing. You don't know, right? You just don't know. But it's at least a guess. It gives you some estimate as to what's going on. And so you can see it's still going. Now I'm going to go ahead and close both of those and stop this query. Now then, okay, that's cool. That's the next lesson. Let me scroll back up here. I want to show you one other thing. Not there, not there. Give me a second. Nope. Let's scroll way back up. One second. Here we go. Now let's take a look at this execution plan one more time. Include the live plan, or sorry, not the live plan, the execution plan, and we've got the and we've got the execution plan right there. Let's do this. Let's save it. Oh, I don't like where that's going. Hang on a second. Let's put it here. There we go. Sorry. Live plan. It was going into my GitHub stuff, and that's no good. And now let's take a look at, remember we had this other execution plan. And this is the last little bit I want to show you today. This execution plan comes up. We can now go, you know what? Let me compare the show plan. And if we go back and get that other plan that we just created, we can compare the two plans. And not only can we compare the two plans, but we get to see areas that are similar. So this nested loop index seek, top index seek, those are very similar shapes with very similar estimates and costs associated. And so the differences on the two plans are out here, but the similarities are in here. If there are multiple similar areas, you will see multiple colors in different places. This is a great thing. Further, if we select, say, the select operator, over here we can now see a comparison between the compile CPU and the compile memory, the compile time, the stats usage. Are they the same between the two plans? And no, in fact, they're not. They're different stats were used to compile the plans. Makes sense in the way that the queries were written. But you can see similarities and differences, places that are the same and places that are different. And you can even do it down here where the differences are going to be a bit more profound, even though these are the similar parts of the plan. Now, in the place where we go where the plan is different, it doesn't then line them up. It can't. So you're then looking at one thing that's different from the others. But if we continue to work at it this way, we can see the same operators in each place. And you'll notice that is a little bit of a bug, right? If you select that and suddenly everything's different. So you're going to find that that gets weird. But reselecting resets. So there you go. We can compare plans. Let me show you one last thing. Let's take a look at which plan was it? Not that one. No, we're not messing with column store indexes again. Takes too long. Let's do parameter sniffing. Let's pluck the plan back out of cache. I think this one's got a problem. Cool. Now let's take a look at this query and this plan. And right click again. And we've got one other little trick. Analyze execution plan. This thing has this thing called scenarios. Oh, and this one, oh nuts, this one doesn't have any data at all. Oh well, I was going to try to show you real quick. It only has a single scenario right now, and it's inaccurate cardinality estimations. I really hope they spend some more time on this and expand it out. But what it does is it will show you in an execution plan. Well, here, let's see if we can generate it this way. Analyze. There we go. Haha. Because we're off. Number of rows returned, 1. Estimated number of rows returned, 72. But because we're off, we see the 7,100% difference down here. And so you can begin to see that this is kind of useful. It gives you some indication of places where the plan is off, and you can start to make some guesses as to what's occurring. So that's the last little bit of tooling that I wanted to show you in terms of tools that help you do execution plans better. Sorry, my nose is itching. Let's see. We need to get to... We did that. Right. All right, so if you want some additional reading, the book, SQL Server Query Performance Tuning 2017, has got lots of information on the optimizer and a lot of information on query execution plans. But if you're really ready to dig in on execution plans, pick up the 3rd edition of SQL Server Execution Plans. The digital version is completely and utterly free. Download it; it's yours. The print version, if you want it, you have to pay for the paper. But everything else is free. So hopefully that would be useful to you. Let me switch back over here to, where am I? There we go. The live stream. Make sure everything's all set. It is. Cool. No additional questions. All right. Well, I'm going to wrap it up for today. That's it. That was part 2 of execution plans. Next week, we are going to go over automation, some of the new functionality inside of SQL Server that automatically tunes query performance. It's all a little bit touchy-feely and weird, but it's still cool and fun. So we're going to go over that next week, and then that will conclude my class on tools to assist you in query tuning. Thanks a lot. My name is Grant Fritchie. You guys have a great day.